Hi, I'm Dr. Aaron Patton, and today we're going to talk a little bit about spray tank water quality. I'm going to share with you what we now know about quality after we've researched this for several years. Now, the first thing we want to talk about is our spray water pH. Now, we can measure spray water pH a few different ways. We can measure it with some test strips. We can measure it with a meter, inexpensive meters, or we could use some fancy equipment to measure it more precisely. But really all we're after here in the turf industry is just to know approximately what our pH is. So a test strip or an inexpensive meter would work just fine. Now, when we think about our water qualities that we have to work with, whether we get our water from municipal water, from a well, from a pond or lake, or even rainwater is something that we can collect in the turf industry. Those are all potential sources for us to spray with. Now, generally, all those sources, with the exception of rainwater, are going to be slightly alkaline or have a pH of probably between 7.5 and 8 most of the time here in the Midwest. But rainwater, because it's not traveling through the earth dissolving some of those minerals that make the water alkaline, will typically have a slightly acidic pH. Now, let's take a look at a few label statements regarding some of these products that we may use in the turf industry to see what they have to say about spray water pH. So the first product we're looking at here, first product label is Scimitar. It's an insecticide, and what we see here is that it notes that a pH of 5 to 7 works best. So if your pH is above this, then they're encouraging you to lower it. The next product we're looking at is a fungicide. This is thiophanate methyl, sold as 3336 flowable fungicide, and we see there that they recommend buffering the tank water pH to between 6 and 7 prior to adding the fungicide to the tank. Now, I do know that this particular product has a little bit of a buffering agent already in the formulation, but there's nothing on the label or the SDS sheet that would indicate that to you. The next fungicide that we're going to take a look at is 26GT. This is iprodione, and it doesn't tell us exactly what the pH is, but it mentions that if the product is allowed to stand in the tank for more than 12 hours, that there may be some breakdown of the product. So that's indicating there may be an issue related to the half-life of this product and how it could be negatively affected by a higher pH. Now we transition to a herbicide. Here we're looking at the monument label, that's trifloxysulfuron, and here we see a statement about not using this product if the pH of your water is less than 5.5, and if it is, you want to raise it to a pH that's close to neutral. Here we have another herbicide, Quicksilver carfentrazone, and this one encourages us to spray it within a range of 5 to 8, which is a pretty big range, but that the product might work best between a pH of 6 to 7. So we've looked at just a handful of labels, but most of the labels out in our industry say absolutely nothing about the pH of our spray tank water. So generally what we know is that most of these products are going to work well in quite a large range of spray water pHs, and it's only a few that mention something specific about pH. Now, Dr. Rick Lattin undertook a study here at Purdue where he wanted to explore the effect of this pH issue on the effectiveness of some different fungicides. So they wanted to look at the different fungicides, different spray water pHs, and then also, does it matter if you spray the products right away or you wait 24 hours to spray them. So he selected 3 fungicides for his trial: iprodione, thiophanate methyl, and metconazole. The 3 pH levels he looked at were 5, 7, and a pH of 9. And then for each of these products, he either sprayed them right away or sprayed them 24 hours later. Now, this research was conducted by his master's student, Trevor Stacy. And the reason these 3 products were selected was because they had a difference in their half-life. So let's take a look at that at this table here at the bottom. Now, all 3 of these products are reported to be stable at a pH of 5. So we have some chemical references that tell us a little bit about how these ingredients might act under certain pHs, and they're all supposed to be stable at a pH of 5, meaning that they'll last a long time in a solution at that pH. Now, when we change the pH to a neutral pH of 7, we see that the iprodione has a half-life that's 1 to 7 days. And so what that means is over that 1 to 7 day period, half, in theory, of the fungicide half of its activity would be decreased because the fungicide would be broken down by the water that it's mixed in. And this issue of what's called alkaline hydrolysis gets worse when the pH gets higher. And here we see at a pH of 9 that the half-life of iprodione is reported to be only 22 minutes. And what that theoretically means is that 22 minutes after you're mixing, only half of the fungicide would be there effectively working to control the disease. We see thiophanate methyl is only supposed to be half as effective 1 day later. And we see that the metconazole seems to be stable across the pHs. So Dr. Lattin set to test out this theory. Are these values that we have on half-lives, are they actually true, and do they work in the real world? So Trevor did a series of experiments out in the field, replicated them, and here's what they found. They found that there was no differences in disease severity amongst the pH levels. So what that means is it didn't matter what the spray water pH was, the fungicide worked effectively and equally well regardless of the pH. What they also found was that it didn't matter whether you sprayed it immediately or waited 24 hours. The fungicides worked effectively either way. And so their conclusion was that the water pH is really not going to have a big impact on your fungicide efficacy. The biggest impact on your fungicide efficacy is the fungicide that you pick. So picking a fungicide that works well on that particular disease was still the most important thing. Now here's a picture of the plots for Trevor's research. You can see some treatments working really well, some not working well. The ones that weren't working well in this particular picture are ones that just had a shorter activity. Now, if we focus in on the plots that look good, what we see is those are our thiophanate methyl plots. This particular area of research plot out at our Daniel Turf Center does not have a thiophanate resistant dollar spot population, and so that fungicide, which while it be older, still works well for us in our research plots. And what you see based on the text boxes and the arrows is it doesn't matter what the pH was. It didn't matter whether you sprayed it right away or you waited 24 hours to spray it. The fungicide was working well. So that means that those half-life data that we found in our publications were misleading or not telling the whole story. So let's think about that a little bit. So why do we read some places say that the pH of our spray water makes a difference, and then we do research like this and it seems to not make a difference? What are the reasons for that? So let's take a look at those reasons. First, most of the time we mix and spray within a few hours, and so that really reduces the likelihood of any potential problem occurring. So that's a good thing that we're already doing and a good way to make sure that you're maximizing the effectiveness of these products. The second issue is that most of the time when we learn about these chemistries, we find out that it's really a big problem with the pH gets very acidic, less than 5, or is very alkaline, greater than 9. And we rarely encounter those types of pHs in our spray water. Other things to remember is that the manufacturer may include some kind of a buffering agent in their formulation, and there's nowhere that they're going to tell you that on the label or the SDS sheet. And so the only way that you know that they've added a buffering agent is to test your spray water before you add the product and after you add the product to your mixture to see if it may be influencing the mixture pH. Now, the other reason, and these last two I think are really important, the other reason that this doesn't seem to be an issue is we put very concentrated levels of these products in our spray water because we're taking them from the jug where they're extremely concentrated, we're putting them in our spray tank where they're still very concentrated, and then we're spreading them out over a large area where they're going to be essentially spread out and dilute. Now, when we think about these pesticides, what we know is that because they're there in very concentrated form, we know that there's usually more there than can be soluble in that spray tank, in the water in that spray tank. So what that means is only part of the herbicide or the insecticide or the fungicide is soluble, and the rest of it is still in a suspension. And so what we know from a chemistry standpoint is this breakdown that can occur in these spray tanks is only happening on the soluble portion and not in the proportion that's suspended in our water. So for that reason, many times when we put something in the spray tank, even if it's subject to breaking down over time, it's only a small portion of what we add to the tank that could be broken down. The rest of it's in suspension and is not being acted upon by these chemical properties because it's not soluble. And then the last reason is if we think about our fungicides, for example, we see that they can break down in certain conditions, certain alkaline conditions. That's true. But the assumption is that if they break down, they're breaking down into something that's not an effective fungicide, and that's not always the case. In fact, with some of the fungicides that we have that are subject to breaking down, what we find is they actually break down into another fungicide that can also be effective against the pests. So because we're basically mixing and spraying right away, that essentially eliminates the risk of there being a problem. And then when we think about these other factors, the fact that we're adding these products to high concentrations in the tank, that sometimes the manufacturers already included a buffering agent in the tank, and the fact that sometimes when these products break down, they break down into something that can also still be effective as a pesticide. It's for all these reasons that our spray water pH ultimately doesn't end up having a big impact on the efficacy of our applications. Now, there's charts that you can find, like the ones shown on the left, from different manufacturers that provide you some clues on when you might need to buffer your water or change the pH of your water to increase the effectiveness of these pesticides. And I think, based on some of the research that we've done here at Purdue recently, that these are overly cautious, overly conservative. And so there's a handout provided for you today that looks much like the picture on the right to show you what's the real story there, with the green being these are products that you can use across a wide variety of pHs, and the yellow indicating that that's a pH that you may need to consider making a modification. And you see that for the vast majority of products, you're not going to need to modify your spray water for that product to work effectively. Now let's switch gears here and talk a little bit about water hardness, because I think that's a bigger issue for us to consider in the turf industry. Now, when we're talking about water hardness, we need to first define it, and we're just talking about a measure of the total concentration of the cations in the water. And particularly, we're talking about calcium, magnesium, and iron being the major cations that can make our water hard. Now, because those are all different elements, but we have to have one common way to measure them, then we measure water hardness in calcium carbonate equivalents. And so those are the units that hardness is measured as. Now, just like we talked about before, we have different sources of water that we might pull from in order to spray with. And we're going to see that just like before, our well, our stream, pond, our municipal water, they're all going to be hard water in the Midwest. And the only soft water source that we potentially have is our rainwater that we may consider collecting. Some operations will collect rainwater and use that to spray with. Now, to measure hardness of your water, it's pretty easy. You can do it several different ways. One way is to just use these test strips. It's a quick way to assess water hardness. A second way is to use a titration kit. These titration kits are fairly inexpensive, and they can also be used to assess your water hardness. And this is the type of kit that a Culligan man or some other person would use if they came to your house to try to sell you a water softener. And then the last thing you can do is send it off for a test. But you need to make sure not to get an irrigation water test, because that won't report hardness. Instead, send it off to the same labs that you typically get your soil tested from and tell them you need a spray water quality test. Now here's just a picture of what some of these strips look like so you can get an idea. And I recommend getting one that measures both hardness and pH, since those are things that we're possibly interested in. Now, the good news about water hardness is that it seems to only cause a problem with our herbicides. So it's not impacting our fungicides, it's not impacting our insecticides based on what we know today. And even with our herbicides, it's only impacting a certain set of herbicides, and those are what we call the weak acid herbicides. And I'll give you a list of those in just a second. So hardness doesn't cause a problem with fungicides, it doesn't cause a problem with insecticides, but it can with herbicides and possibly with certain plant growth regulators. Now, how hard does your water have to be to cause a problem? This is a common question that we'll get. And it depends on the herbicide. So we know glyphosate, for example, can be more easily antagonized by hard water. So with glyphosate, anytime our water hardness is above 150 parts per million, then we need to consider to condition it in order to improve its effectiveness. Now, with other herbicides that we might more commonly use in the turf industry, like 2,4-D, for example, then that is one that it seems like our water needs to be a little bit harder before it starts to become a problem. So let's take a look at these two herbicides in a little bit more detail so we can kind of understand how antagonism occurs and then how we might remedy it. So here's the list of our weak acid herbicides. We have 2,4-D and dicamba, common broadleaf herbicides that we might use. We've got glyphosate there, a common herbicide that we use for renovation projects and just controlling weeds in landscape beds and so on. And then we have several other herbicides in there, some other broadleaf herbicides, some sedge herbicides, some grass herbicides. So you see there's several herbicides, and this isn't a complete list, but a list of the ones we use most commonly in the turf and ornamental industry. And all of these can be subject to hard water antagonism because of their chemistry as a weak acid. Now, in order for hardness to occur, we have to have divalent cations in the water. So we have lots of cations in the water. Cations are just things that are positively charged, but it's really the divalent ones, the ones that have a double positive charge. They're the ones that can cause us problems with our hard water, and you can see those listed there. And it's particularly the calcium. That's the one that's most abundant in our spray water and the one that typically causes us the problem most often. Now, so what's going on when this causes hard water is that calcium molecule can basically bind two herbicide molecules together, creating this kind of big clunky molecule that doesn't work as well as a herbicide. So take, for example, the glyphosate molecule that's on the left. If we take that glyphosate molecule and put it in hard water, what will happen is the calcium will bind two glyphosate molecules together, and again, create this big bulky molecule that doesn't work as well as a herbicide. So this is what this may look like if we kind of take a look at this drawing. So we have glyphosate having a negative charge, being this big molecule. We have these orange divalent cations like iron and calcium and magnesium in our water, and when they interact with the glyphosate, then basically those divalent cations can bond two glyphosate molecules together and creating this product that doesn't work very well. So this is what this may look like. Okay, so let's say on the middle plant here we have an untreated weed, velvet leaf in this case. It doesn't really matter what the weed is here, and we see it growing nice and tall. Now if we spray a low rate of glyphosate on this weed with deionized water, we see that the glyphosate is working to stunt this weed and hopefully ultimately to kill this weed because it stopped it from continuing to grow. So in this example, all these weeds were treated at the same timing. But if we take that same weed and we spray glyphosate, but instead we use well water, we see that that weed is growing quite large. It's almost as big as the non-treated weed, certainly a lot bigger than the glyphosate, the weed that was treated with glyphosate and deionized water, water that was clean of any cations and minerals. So we know there's something in that well water that's causing that glyphosate not to work as well, and that's that calcium, iron, and magnesium that we mentioned. So to reduce the influence of hard water on our herbicides, we can use a water conditioning agent to remedy this. And the water conditioning agent that's most commonly used and the least expensive is ammonium sulfate. And then at the bottom there you have the formula for ammonium sulfate listed, and we're going to talk a little bit about that here on the next slide. So on the left there we see ammonium sulfate. It's a sulfate anion, which has a double negative charge, and 2 ammonium cations. And each of these ammonium cations has a positive charge. And when we put that ammonium sulfate, which is water soluble, in our spray tank, what happens is that sulfate anion will bond with the divalent cations in the water, the calcium, the iron, the magnesium, and the ammonium cation will bond with the glyphosate molecule, creating an ammonium salt of glyphosate, and that ammonium salt of glyphosate will work really effectively as a herbicide. Now, there are a few label statements on these glyphosate products that will describe this to you, although they don't describe it in great detail. So let's take a look at one of these. So here we have the QualiPro product, glyphosate TNO. It says, has a statement on the label about ammonium sulfate. It says adding 1 to 2% dry ammonium sulfate by weight. Okay, 1 to 2%, that sounds pretty simple. It says to add that by weight, and then it gives us a number here, 8.5 to 17 pounds per 100 gallons. Where'd that number come from? We're going to talk about that in just a second. But it says adding that may improve the performance of glyphosate, particularly under hard water conditions. And so that's what we're wanting to do. Now, other glyphosate labels will have similar statements. Like here's a Lesco product, and if we see the small text at the bottom, we see the exact same verbiage that we saw on the previous label. So where did that 8.5 and 17 pounds of ammonium sulfate per 100 gallons of spray water, where did that come from? Because the label said to add 1 to 2%, okay? And that comes from the fact that that ratio is determined on a weight by weight basis. So what we know is that 100 gallons of water weighs 834 pounds. So when we think about, well, what's 2% of 834? Well, that's going to be equal to 16.7 pounds, or rounded up, 17 pounds. So that's where that 17 pounds of ammonium sulfate per 100 gallons of water come to. That's 2% of the weight of the water itself. And again, adding that ammonium sulfate, that dry crystal, which is water soluble, to our spray tank will work just fine because it will solubilize in the water. Now, when you're adding that to the tank out in the real world, what you can do, and what I recommend, is just dissolving your ammonium sulfate in a 5-gallon bucket. It will dissolve faster if you use warm water, but you can certainly use just a higher volume of cold water. And then pouring that into your sprayer through a screen to make sure there's no impurities in that is best. But when they sell this ammonium sulfate, then it's going to come in a crystal form that's going to easily dissolve. And I'll show you a picture of that in just a second. So ammonium sulfate, it is a fertilizer. It has a 2100 analysis, but in this case we're using a very small amount of it, not enough that really provides us a fertilization, but just enough to work as a conditioning agent for our water. And here we see that if we did some math, we're only supplying anywhere from 0.01 pounds to 0.07 pounds of nitrogen per 1,000 square feet, depending on our spray volume. Now, if you didn't want to use dry ammonium sulfate, there are liquid products on the market, so you could use one of those as well. And here's just a picture of what these bags of ammonium sulfate look like. They're sold in 51-pound bags, and so that you can easily dissolve them in your water. It is crystal form, and the 51 comes into play because at 17 pounds of ammonium sulfate per 100 gallon, this 51-pound bag would be the exact amount that you would need for a 300-gallon sprayer. Now, what about 2,4-D? I mentioned that as being another one that can be problematic as a weak acid herbicide. So let me kind of briefly share with you all that we've learned about this over the last 3 or 4 years. So the first thing to know is that hard water can and does antagonize 2,4-D, and we've shown this to be true in several of our research projects. The second thing is that the ammonium sulfate does successfully overcome hard water antagonism when we use it at these adjuvant rates of anywhere from 8.5 to 17 pounds of ammonium sulfate per 100 gallons of water. Here's just an illustration or a photo from one of our research studies showing a non-treated dandelion on the left. In the middle, we see a dandelion treated with 2,4-D, but in hard water. And we see that dandelion looks pretty big and healthy. And then on the right, we see a dandelion treated with 2,4-D in hard water, but where we've added ammonium sulfate, and we see that ammonium sulfate helps that herbicide to start working to kill the weed. Now, a third thing we've learned in our research with 2,4-D is that your water hardness needs to be at about 400 parts per million or higher in order for this antagonism to occur. So here's just a chart showing one of our greenhouse studies. And the blue line shows you that when you have AMS or ammonium sulfate in your spray tank, that you get equal control, in this case, or an equal reduction in the root size of the dandelions, regardless of your water hardness. But if we follow the green line, what we see is if we don't add ammonium sulfate to our spray tank, as our water gets harder, then the size of the dandelion root gets bigger, basically telling us that our weed control is getting poorer. And we see the difference between these two lines occurring at about 400 parts per million. Now, we've also done this research in the field, and this is what we see in the field. We see that if your water hardness is 0 or 225 parts per million, that whether you have ammonium sulfate in the tank or not, you get equal weed control. But when we start to go higher with our water hardness, what we see is we start to lose control when we don't have the ammonium sulfate in the spray tank. And then likewise, we see that when we add ammonium sulfate to the spray tank, when our water hardness is higher, above 400 parts per million, we start to get better control of our dandelions. In this case, twice as good a control of our dandelions. All right, a fourth thing that we've learned is that this water hardness, this hard water antagonism, is only a problem when we're using soluble formulations of our herbicides. So these soluble formulations are going to be common products that we use and often are amine products. So our amine-based formulations are often formulated as water soluble, and these are the ones that can be antagonized. If we're using an ester formulation, those are usually emulsifiable concentrates, or if we're using some of these new formulations which are sold as EW, or emulsification in water, then those products, because they have an emulsifying agent in them, they're not subject to the hard water antagonism. And that's maybe a longer story for another day, but what you need to remember is that when you're using these soluble formulations of broadleaf herbicides, especially those with 2,4-D, they can be subject to hard water antagonism. Now here's just a heat map from some of our research showing the level of control you might get with these different formulations on dandelions. And we see what we're after is the green squares there. And that shows us that if we use soft water or rainwater, that we can use any of these herbicides just fine. But when we use hard water, we have to be using an EW or an SC formulation or an EC formulation in order not to have the hard water antagonism, or we have to use ammonium sulfate when we use that soluble formulation in order to counteract the hardness. All right, a fifth thing we learned from our research is that iron can also antagonize 2,4-D. And so here's some field work that we did showing that if we spray 2,4-D by itself, it works really well compared to the non-treated in the bottom right corner. But when we start adding different iron sources, whether they be a chelated iron source or water-soluble iron source, our 2,4-D doesn't work as well. So that iron, even in our iron fertilizer products that we might add to the spray tank, can also interact and antagonize with the 2,4-D. So in conclusion, water impacts the performance of some of the products that we use. We have limited data on all the possible combinations. Some labels inform us, but most do not. And so checking the quality of your water is well worth the money considering the investment you're making in these products. For fungicides and insecticides, water quality is not as big of an issue with our current chemistry, but when we're applying our herbicides, we may need to condition the water with something like ammonium sulfate to improve the efficacy. So I hope this presentation has been helpful for you, and thank you for joining us for this online virtual event.